Example 10. A car is traveling east on the interstate. A highway patrolman is parked 90 meters north of the interstate. The patrolman takes a radar reading and finds that there's a car 150 meters from his position, and the distance separating them is increasing at a rate of 72 meters per second. We want to find the speed of the car at this moment. So let's start by getting a diagram out, right? Let's say we've got an interstate that looks like this, right? Given by this horizontal line. And I've got a patrolman right here, which is due north of the interstate. And we've got a car, okay, which is traveling towards the east. And we know that the distance separating the patrolman and the car at this particular point in time is 150. But don't come along and label this distance as 150, okay? Because we know that the car is moving towards the east. So that means that the range or the distance separating the patrolman from the car is increasing over time. So therefore, we should relate to this variable, let's say by the letter R standing for the range. And let's let the distance of the car away from the point O be equals to x. So the rate at which x is increasing represents the speed of the car, okay? And that's what we want to find. So dx dt is what the question seeks. And we also know that r, which is the distance between the patrolman and the car, is increasing at a rate of 72 meters per second. So in other words, dr dt is equals to 72. So if we check this out, right, we know that the chain rule necessary to link all my differentials together is given by dx dt is equals to dx dr times dr dt. So in other words, what I need in order to find dx dt in this case is I need dx dr. And to find dx dr, I need an expression that connects x and r together. Again, we know that, of course, the patrolman, remember, is 90 meters away from the interstate. Okay, so this distance does not change. X does increase with respect to time, and r also increases over time as well. But we know that if this is a right angle triangle, then at any given point in time, we can say that x squared is equals to r squared minus 90 squared, right, by Pythagoras. So in other words, x is equals to square root of r squared minus 90 squared. And what this allows us to do is differentiate this expression for dx dr. So if I differentiate this expression, I'm going to get dx dr is equals to r over square root r squared minus 90 squared. Okay, hopefully we don't have any difficulty in differentiating expressions like this by this point in time. And with this, right, I can say that dx dt, which is equals to dx dr times dr dt, can now be calculated because we know that dx dr, okay, which is equals to r over square root r squared minus 90 squared. We know that dr dt is given by 72. So when r is equal to 150, because we're looking at a particular point in time, right, we want to find the speed of the car at the moment when the car is 150 meters away from the patrolman, right? So when r is equals to 150, we know that dx dt is equals to dx dr, which is this expression here. We take r equals to 150 and we substitute that in. So that's going to be 150 over square root 150 squared minus 90 squared. So that's dx dr times dr dt, which is equals to 72. And of course, if we plug all of this into the calculator, our final answer is going to be 90 meters per second. Okay, and some of us might realize that this is actually a ridiculously fast speed, right? If we want to turn this into kilometers per hour, what we do is we take 90 times 3.6, okay, and that's going to give us a speed in excess of 300 kilometers per hour, okay, which is quite ridiculous. So that being said, this concludes example 10.